Hello and welcome to Cognito Key. What if I told you there's a kind of digital traffic jam that can bring even the most powerful computers to a complete standstill? Well, today we're going to untangle exactly that, the super frustrating problem known as deadlock.
You know that feeling, right? You're stuck in a crazy traffic jam. Absolute gridlock. Every single car is waiting for another car to move, but that car is also waiting, and nothing happens. It's just a total standstill.
Believe it or not, our computers can get stuck in the very same kind of mess. When you have multiple programs running at once, this is called a deadlock. It's where different processes get completely frozen, each one waiting for a resource that another waiting process is holding on to. It's a digital standoff where nobody wins.
Okay, so let's get into the nitty-gritty. A deadlock isn't just some random fluke. It's actually more like a recipe. A very specific recipe that needs 4 essential ingredients, or conditions, to all be present at the exact same time.
And here they are: mutual exclusion, hold and wait, no preemption, and circular wait. Now the interesting part is, if you want to prevent a deadlock, you just need to break one of these 4 conditions. So, let's break down what each of these really means.
First up, we have mutual exclusion. Now, this one's pretty straightforward. It just means that only one process can use a particular resource at a time. A printer is a perfect example. If it's printing a document, any other program that wants to print just has to get in line and wait. Simple as that, one at a time. Next is hold and wait. Imagine this. You have a pen in your hand, but you need some paper to write on. But someone else is using all the paper. So what are you doing? You're holding the pen while you wait for the paper. A process does the exact same thing. It holds on tight to at least one resource while it waits for another one to become available. Condition number 3 is no preemption. Think of it this way. Once a process has a resource, you can't just snatch it away. The operating system can't just jump in and say, "Hey, your time's up, give that back." Nope. The process has to finish what it's doing and release the resource voluntarily. And that brings us to the final piece of the puzzle, the one that ties everything into a big, unbreakable knot: circular wait. This is where you get a group of processes all waiting for each other in a complete circle. P0 is waiting for a resource from P1, P1 is waiting on P2, and P2 is waiting for the very resource that P0 is holding. It's an endless loop of waiting.
So we know the 4 ingredients for deadlock, but how can we actually see if it's happening? Well, for that, we have a really cool tool called a Resource Allocation Graph. You can think of it like a live map of the system, showing us exactly who has what and who wants what at any given moment. The map uses a really simple visual language. The processes, the active programs, are shown as circles. The resources they need, like a CPU or a file, are shown as rectangles. And if there's more than one of a certain resource, say 2 printers, we show them as little dots inside that rectangle. And the arrows tell us what's going on. If an arrow points from a process to a resource, that's a request edge. It means, hey, I need this. If the arrow points from a resource to a process, that's an assignment edge. It means, okay, you've got it. It's a super clear way to see the entire flow.
All right, now that we know how to read the map, it's time to play detective. We're going to use this graph to actually hunt for a deadlock in action.
So let's look at this system right here. We've got process P1, which is holding on to resource R2, but it's waiting for R1. Meanwhile, process P2 has R1, but it's waiting for R3. And finally, process P3 is just holding R3.
So, looking at this whole picture, would you say this system is in a deadlock? The answer is actually not yet. Sure, P1 and P2 are waiting, but there's a way out. If P3 finishes its work, it will release its resource, and then P2 can grab it and move forward, which breaks the chain. But let's change just one tiny thing. What if process P3, while it's still holding on to its resource, suddenly decides it needs resource R2, which, if you remember, is being held by P1?
And boom, that's it. That's the moment of gridlock. A cycle has now formed in our graph. P1 is waiting on P2, P2 is waiting on P3, and now P3 is waiting on P1. This circular chain of requests is the smoking gun. It's the absolute proof that a deadlock has occurred. Okay, let's take a step back and quickly go over the key takeaways from all of this. Why is understanding deadlocks so important?
So just remember, a deadlock isn't some random event. It's that perfect storm where all 4 conditions meet: mutual exclusion, hold and wait, no preemption, and that final nail in the coffin, circular wait. And the resource allocation graph is our best friend for spotting it, because a cycle in that graph is the telltale sign.
So this brings us to the really big question. Now that you know how to spot a deadlock and you understand its ingredients, how would you go about preventing one from ever happening in the first place? It's a really fascinating challenge for anyone designing complex systems. Thank you so much for joining me on Cognito Key. If you found this explainer helpful, please hit that like button, subscribe to the channel, and share this video. We'll be back soon to make more complex topics simple. Until then, keep learning